Good morning to everybody, and we start the Excel 2018 with the first keynote that comes from the Professor Rick Kazman. It's a pleasure for us that you accept this keynote. Professor Rick Kazman, I think that he don't need any kind of presentation. But I would like to, of course, present them. It's a very known for us, and we have all of us read the papers, books, and all this distribution of knowledge that he has provided to our community. Professor Rick Kazman comes from the University of Hawaii. Is a research scientist at the Software Engineering Institute of Carnegie Mellon from USA. His primary research interests are, of course, software architectures, design and analysis, software visualization, and software engineering economics. Kazman has created several tools that help us to support software architectures, such as the software architectures analysis method, or the software architecture trade-off analysis method, or cost-benefit analysis method. He has, as I mentioned, more than 200 publications in software architectures in this area, and we have the lack of being here with us, and we are very proud of this. So please, Dr. Rick Kazman, when you want.
Okay, thank you, Jennifer, and to the committee for inviting me to give this keynote talk. It is, of course, a great honor to be asked to give a keynote talk. This means a couple things. It means I'm old. I've been doing research in software architecture for more than 25 years. My first published paper in architecture was from 1994, in Sorrento, if any of you remember that, back that long. And this is, as I say, the second thing is it's a great honor for me to be asked to give this talk. And I know many of you here, but certainly not all of you, so I guess part of the privilege of being asked to give a keynote talk is I can be a little bit self-indulgent at the beginning, and I want to tell you a little bit about myself, in part to explain how I got here and how I got to be interested in the things that I'm interested in. So a brief self-indulgent history. So I'm originally from here. I don't know if any of you recognize this, but this is the beautiful city of Toronto, Canada, in the summer when it looks beautiful. And I studied here, a little bit more of an obscure reference. If any of you recognize this gorgeous piece of brutalist architecture, this is the math building at the University of Waterloo. So I studied at Waterloo, which is just about 130 kilometers away from Toronto, but I didn't study what you would expect. I actually majored in English and minored in music. So how did this get me here? Excellent question. I have a lot of interests, and fortunately, this life has been good to me and has allowed me to explore many of them and combine many of them. So after doing this degree in English and music, I did a master's degree in English, and then I decided I needed to find an actual job. And the one skill that I had from my undergraduate degree at Waterloo was I could program. I knew math, I knew computer science, and so I decided to go back and get a master's degree in computer science, which I did at the University of Waterloo, and that led me here. As part of my master's degree, I worked on turning the Oxford English Dictionary, transforming it from a book into a database. And so my research led me to Oxford, and specifically to the Oxford University Press, where I worked on finite state transduction of the Oxford English Dictionary, allowing me to combine two of my loves, English and computer science. And this was wonderful. And this eventually led me to do my PhD at Carnegie Mellon University, where they had a brand new program in computational linguistics, again, allowing me to continue this merging of my two loves. While I was there, however, I started spending more and more of my time across campus. In this place, the Software Engineering Institute. And so while I was doing my PhD in computational linguistics, I started actually getting more interested in software engineering than in my own PhD. In 1989, I believe it was, I heard my first talk on software architecture, the first time that I had heard those words adjacent to each other, and that was a talk given at the Software Engineering Institute by Mary Shaw. And eventually, via a series of jobs, it ended me up here. For those of you who don't recognize it, this is Waikiki. So now I'm a faculty member at the University of Hawaii. Again, to quote an old song, what a long, strange trip it's been. Where I spend my time, of course, on the beach. Okay, so you may be asking yourself, what has this got to do with anything other than being this indulgent personal history? So I guess three things. First of all, I like multidisciplinary things. I'm at least as interested in people and contextual factors as technology, and this has taken me many places. So my personal evolution as a software engineering researcher began with this paper, SAM, the Software Architecture Analysis Method, which, as I said, was published in ICSE in 1994. And at the time, architecture was still quite a nascent discipline. There were very few papers or books at that time. And when you looked for papers in the research literature that said something about architecture, people would just make claims about their architecture. My architecture is better in terms of modifiability and performance, and my architecture is more robust. And SAM was an attempt to try and put some rigor into measuring these claims. And so we came up with this idea of using scenarios as architectural test cases. And we applied a set of scenarios against an architecture to try and assess, in the case of SAM, it's the modifiability of that architecture. SAM eventually evolved to the ATAM, so we realized that there were other quality attributes of interest. People didn't just worry about the modifiability of their architecture, but its performance, its security, its testability, its interoperability, and so forth. And so we started to think about using these scenarios as more complex test cases. We tried to put more rigor behind the method. We were striving for repeatability. If you aspire to be an engineering discipline, then the tools and techniques that you create should be usable by people of intelligence, training, and average skills. You should not have to be a super expert to use a tool or a technique or a method. And so this caused us to try and make the method more rigorous, to create more structure, templates, reusable chunks of knowledge, checklists. And so we became focused on the usability of this method that we were creating. And so that was pretty good, but still the outputs of the ATAM were highly dependent on the skills and training and knowledge, background knowledge of the people who were leading this method. Also, ATAM produced a set of risks. And risks were technical in nature, typically. And one day, I had done an ATAM on a medical information system. This was a system that was being built by Siemens, And we did this ATAM, and after the ATAM, we were sitting around chatting with the architects, feeling pretty good about ourselves. We had produced a long list of risks and trade-offs. And I started, again, feeling pretty good about myself, I started suggesting some architectural improvements to the architects of the system. You know, well, here's how you could address this risk, and here's what you should do to address that risk. And every time I made what I thought was a clever suggestion, the architects rejected it. And they said, well, we can't do that. That'll blow our budget. Or we can't do that. We won't meet our next deadline. Every time that I had what I thought was a clever idea, I got slapped in the face by reality, by cost and schedule. And so this caused us to create our next method in this series called the CBAM, the Cost-Benefit Analysis Method. And this allowed us to compare or to analyze architectural strategies, architectural approaches, in terms of their costs and in terms of their benefits so that they could be prioritized. So we started to get more and more interested in being able to quantify architectural approaches, the costs and the benefits of these approaches. And so we took solace in this kind of reasoning, that we really needed to be able to express our knowledge in some sort of numbers so that we could be more rigorous about comparing it. But in the end, it was still garbage in, garbage out, right, as are most methods in software engineering. We were dependent on the knowledge, the inputs of the architects to tell us to get good outputs. And so, of course, there's no sense being so precise if you don't know what you're talking about. And so this was still a problem. This was the heart of the problem, really, with these kinds of human-oriented methods that we have been working so hard to create. So my focus today is really more on automated software engineering, to take the human to some extent, you cannot do it entirely, but to take the human to some extent out of the loop and to automate as much of the analysis as possible so that it is more repeatable, more predictable, so that you can run larger numbers of empirical studies. So tools are not an end in and of themselves, but a way of extending our reach and a way of becoming more objective. And if these empirical studies are done right, this becomes the basis for replication packages so that we can do reproducibility, and this allows us then to talk with more confidence about costs and benefits, about trade-offs, and to address the kinds of issues that industry really has. We are software engineering, not software science. And so we need to concern ourselves with problems of practical significance, with tools that are actually usable by people in industry. And I'll be talking a little later in the talk about the kinds of transition to industry that we've been working on, trying to get these ideas, these theories, translating them into tools and eventually into practice. Because, to quote the great Yogi Berra, in theory, there's no difference between theory and practice. In practice, there is. So we really needed to work with industry, and we felt that this has helped us enormously and kept us humble, right? I was guilty of the sin of pride in that ATAM with Siemens when I thought I knew so much. And reality slapped me in the face. And this, in turn, has changed the way that I view research. So, again, I'll take a step back before I dive into my research. There's thousands of software engineering research papers published every year in our many conferences and journals, more than 100 conferences and journals in software engineering each year. But the feedback that I get from practitioners is that the vast majority of this research doesn't actually help them, doesn't actually address their problems. And by the way, I have to say I am really pleased extremely pleased that there's Industry Day here tomorrow, because I think this is exactly the sort of thing that every software engineering conference needs to be doing, is inviting industry in, collaborating with industry to ensure that we are kept honest, that we're kept on the straight and narrow. So how do I know this? And what makes a piece of research valuable or useful? So a couple of years ago, I did a survey of practitioners along with Anthony Tang. We surveyed 61 practitioners, and we asked them if they had read any research papers from conferences, our conferences or journals, in the last 3 years. And only 19 of them, 31%, said that they had, but when we pressed them, it turned out that only 4 of them could name one of those 100, a true research journal or research conferences. The other ones named trade publications. They maybe had read or attended a QCon or an O'Reilly conference or something like that. And so our conclusion from that is there was a gap. There was a gap between the kinds of research that we as a community were creating and the real needs of industry. Contrast this with medicine. The average internist, the average practicing doctor, spends 4.5 hours per week reading medical journals. Right? There's a gap. There's a huge difference in terms of how well we as researchers are working with and affecting industry. They don't seek out academic results, and we're not adequately communicating our results to practitioners. And I think that again, I was guilty of this, that we don't really understand in many cases the true needs of industry and even of existing solutions in industry. Industry marches along without us and creates its own technologies and its own tools. And so it is up to us to align ourselves, align our work with industry, align our assumptions with industry. And part of this, of course, is the nature of our work. I think that we're dealing with an incentive misalignment. As academics, and I know not all of you are academics in this audience, but as academics, we're incentivized to write papers, journal papers, conference papers, and to get citations of those papers and to get grants, not to have that research that we create adopted by industry. So there is an incentive misalignment here. As a consequence, much of our research may be irrelevant. It may disregard the practical constraints, the real constraints, again, as I did, of solutions that work in the real world. We may not understand the context in which our theories and tools and methods are applied, and hence they're not going to be useful. And here's something that, as a reviewer, I often gripe about, is that very few research papers really attempt to evaluate the costs, the benefits, and the risks of the solution that they promote. Is the benefit of this tool or this technique that you are promulgating worth the trouble, worth the effort? Is this going to be usable in the real world? So last year, there was a really nice paper published in IEEE Software by Lionel Briand, and he talked about context-driven software engineering, which he defines as research focused on problems defined in collaboration with industrial partners and driven by concrete needs. And I'm using my privilege as a keynote speaker to make an argument, a plea for more of this kind of research. And the argument that Lionel makes in this paper is that the applicability of research depends to a large extent on contextual factors, human factors like the background or education of an engineer, organizational factors like cost and schedule constraints, domain-related factors, perhaps compliance to standards. So given that background, that bully pulpit, I'd like to talk about where my research has moved in the past few years to attempt to focus on these kinds of goals, these kinds of constraints. And this is on measuring and managing architecture debt. So this is your average software project. If you work with people in industry, you recognize this picture or the metaphor implied here. The boat is leaking, but you keep paddling. You, the developers of the project, keep paddling. And the question is, why? Why would you not stop, pull the boat onto the shore, bail the water out, and fix the leaks? And there's a couple reasons. One is the illusion of progress. We're working hard, maybe we're working harder than ever, and we are moving forward a little bit. We are still able to make some forward progress. And we typically don't measure the degree to which we are in debt, we are underwater, we are slowed down by the accumulated debt of the decisions that have been made over the years. And the claim that I'm going to make is that this debt is due to the incremental accumulation of architectural flaws. Little tiny design mistakes that programmers make innocently because they're busy doing their real job, which is implementing features and fixing bugs. And so what are architectural flaws? Well, we've all seen them, we all know them. You've probably heard terms like anti-patterns or architectural anti-patterns, and we see these in real life, right? You see the big ball of mud, right? Tangled mess of code, the God class that tries to do everything and is involved in every part of the system. There are interface mismatches or mismatched expectations, mismatched assumptions from one part of the system and another. There are designs where context really was not carefully considered. This is a picture that I took at ICSI in Argentina. So this isn't a joke. This is a real men's room. Somebody designed this, right? Or it evolved. So to me, the grand research challenge then is, how do we measure the health of an architecture? How do we know when an architecture has eroded to a point where we need to do something about the debt? And that means refactor. And refactoring is really difficult. It's really difficult to get approval for refactoring in industry. It's difficult to convince the boss's boss that you should spend a lot of money to implement no new features. Right? That's what refactoring is. And that's the business case that you have to make to management. And it almost never works. Almost never works. So to overcome this inherent bias that your boss's boss or the developer's boss's boss is probably a finance person, a money person, and so you have to make an argument in the terms that they understand. And to do this, again, in a disciplined way, in an engineering way, we want to make this process automated so that we take as much as possible the human out of the loop, that it's repeatable, that it's empirically justified. So I've been working, this is now what I'm going to talk about from here to the rest of the talk is research that I've done with Yunfang Tsai at Drexel University and some other colleagues. We've been doing this for the past 8 or 9 years. Over that time, we've built up a pretty good empirical basis in projects analyzed, case studies, and so we have now a lot of projects that we can use to compare an individual project. We can essentially do what doctors do in creating a health chart. If you have a child and your child is 2 years old, 3 years old, your doctor will say, oh, your daughter is in the 90th percentile for height and the 60th percentile for weight, right? So you can compare against the basis and say, is this a problem, right? If they're in the second percentile, maybe there's a problem that you need to look at. Without this empirical basis, it's difficult to just look at a number and say, my child weighs 27 kilos. Is that good or bad for a 9-year-old? I don't know. It's a number. So what we do to make this process repeatable, our workflow, is that we have a set of data collection tools where we scrape up data from projects, data that projects typically have available, their source code, of course, their revision history, their issues, from their issue or bug tracking system. We analyze those artifacts to try and determine the architectural flaws, and then we follow that up with feedback from practitioners to determine whether this information was correct, whether it reflects their understanding of the architecture, whether it's useful to them, whether it provides insights to them. So we have a set of tools that we've created. This was initially called Titan. Now there's a second generation of these tools called Deviate. And we extract all this information that I just mentioned, the source code, the revision history, the issues from the issue tracking system, and we generate a number of representations of this information where we can analyze the dependencies between these artifacts. So for source code artifacts, there are structural dependencies, and we create an SDSM, a structural design structure matrix. For history, we can create a history DSM, what we call an HDSM, which is a design structure matrix that shows you the historical couplings between artifacts. So if, for example, two files are regularly checked in together, you don't know why, you just know. If you look at the revision history of the project, whenever file X is checked in, file Y is checked in. Whenever X is changed, Y needs to be changed as well. There's something going on there. So we call that history dependency. And we look at that. And then we calculate a number of measures. We generate a number of reports. I'll show you some of these in a minute. And then finally, we collect feedback from practitioners via surveys and interviews. So as I say, for data collection, we grab dependency, history, and issue information. History allows us to see things that you can't see from a static analysis. So when you reverse engineer code, you can see the static dependencies. A inherits from B, A calls B, A depends on B. But when you look at history information, you can see different kinds of dependencies, semantic dependencies, right? A and B both depend on some knowledge of the same file format or encryption scheme or some sort of implicit dependency. Or A and B are communicating, but via some dynamic mechanism, maybe a pub-sub, and you're not going to see that in a static analysis. So history gives us a different insight into the dependencies. And then issues tie everything together so that you can relate these structural dependencies and these historic dependencies to bugs and to changes. When we look at a set of files, we can see, is this relationship between this set of files problematic? Is it generating lots of bugs? Is it generating lots of effort in terms of the lines of code committed? So what we do with this information is we create something called the design rule space, or DR space, which is an architectural view. It's a subset of the system's files. A DR space is led by what we call a leading file. There's a file, typically an important abstraction in the system or an important interface in the system. And there are many other files that depend on that leading file. And we cluster these together. We have an algorithm called the design rule hierarchy algorithm, which is a clustering algorithm to create these DR spaces. And this allows us to understand architecture via a set of dependencies. Every non-trivial software system, everything that has some complexity, so forget Hello World, but real software systems, contains multiple design spaces. So you can look at the design space for each feature implemented or for each pattern that is applied or for each quality attribute that's being addressed. Because it is multidimensional, because a single source code file might participate in a pattern and participate in a feature and might participate in achieving some quality attribute, every file can participate in multiple DR spaces. These are multiple views of the system, and so architectures are, we like to model them as overlapping DR spaces, and we visualize them, I'll show you in a moment, as design structure matrices. So once we've collected this information, we then want to measure these architectural structures. A structure is just a structure. It is neutral. We want to apply some measures of quality so that we can compare and contrast. We can determine thresholds between healthy and unhealthy, that sort of thing. By applying this kind of analysis, we can find hotspots, areas of the architecture that are historically proven to be troublesome. You'll see in a minute we can pinpoint these hotspots that are the sources of large numbers of bugs, large amounts of effort, large numbers of security problems, and so forth. And finally, we use this to quantify debt, right? In the end, the programmer or the architect has to justify their time to their boss or their boss's boss. And that person is typically a money person, not a software person. And so we need to quantify this and to say, these architectural flaws, they are costing you. This is a ball and chain around your leg, and you can improve your business by refactoring, by paying down this debt. So we've got one of the ways that we measure and monitor is via some metrics. In particular, I'll talk about the decoupling level metric that we first presented 2 years ago at ICSI. So decoupling is based on the idea that modules should be small and independent, and that a well-modularized system should have lots of true modules, small independent modules. So this is based on the Baldwin and Clark's design rule theory, this notion of an architecture as a set of modular structures with design rules that keep structures independent from each other. So this is a representation of a toy system in a DSM. In the decoupling level metric, what we want to find is a system where you have lots of small modules decoupled in the lower layers of the architecture. So in this lower right-hand corner, we have small modules that are not dependent on each other. They're independent from each other. And the more of these that you have, the higher the value. If you think of a system of plugins, right? You've got a core, your plugin architecture, and then the individual plugins are what give your architecture value. And the more you have of those, the higher the value. You know, think App Store, right? You have a platform. The things that people care about are the apps. That's what give value. And those things should not depend on each other. The upper layer modules, you want those to have few dependencies between each other. Again, the smaller the module, the higher the value. And so we measure these relationships between the modules, and we turn this into a metric, and we score each architecture on this decoupling level value on a scale of 0 to 100, where 100 is the best, 0 is the worst. And we essentially have created a health chart. So in this 2016 paper, we analyzed 129 projects, 108 open source and 21 industrial. And we can start to talk about what's a normal project. So the average commercial project had a decoupling level of 54. The average open source project had a decoupling level of 60. But you can see the minimum number, 14 and 15, is pretty similar. So there wasn't a big difference between open source and industry projects. So the best DL that we ever saw, 93%, was from an industrial project. That's only slightly better than the best open source project of 92. But what we can do with this now is take any new project and map it onto the health chart, just like saying, is my daughter too small for her age? And so here's a project that had a decoupling level of 29% in the 10th percentile, and in interviews with the architecture team, this is an industrial project, they did describe having severe maintenance difficulty. We can also use this to look at the evolution of a project over time. So if you can build this into your nightly builds, you can calculate this measure and you can see, are we going up, are we going down, how are we doing over time? So this was an industrial project which we analyzed it over a period of 6 years. And what you can see is initially the DL went up. This was when they were transforming the project from a prototype into a real product, and so they spent a lot of time on improving the design of the project. Then over the next year or so, they added more and more features, and the DL slowly degraded but eventually stabilized. And then they decided to do a refactoring. And at this inflection point, number 3, they did the refactoring, and the decoupling level went down, which is not what you would hope. And this is because they got the refactoring wrong. The programmers didn't really understand the intent of the design patterns that were chosen, and they actually made the system much worse. And eventually, the DL increased from 48% up to 62% when they realized the consequences of their original refactoring, and they cleaned up the technical debt. So this is a kind of health chart over time, just like you might track your cholesterol level or your blood sugar level over time to determine whether you need to go on medication or not. Another kind of health measure that we use is we automatically detect flaws, and we can automatically detect 6 kinds of flaws: unstable interface, modularity violation, and so forth. I will show you some examples, but the point here, the reason that we're analyzing and collecting these, is that these flaws are highly, highly correlated with bugs, changes, and churn. Files that participate in higher numbers of flaws are buggy, they cause a lot of problems, they cost a lot of effort. So let's take a look at these. One flaw is unstable interface. What you see is an important file, in this case utils.fbutilities, and there are many other files that depend on this file and co-change with the file. So the notation here is DP means depend, then there's a comma, and the number after the comma is the number of times that that pair of files, file number 2, fbutility, and the other files in that column co-changed. So fbutilities and database descriptor co-changed 44 times, for example. So that's an unstable interface. You have this important file, lots of other files depend on it, and they're changing constantly. The interface is changing, and the files that depend on the interface are changing. Not what you want. You want interfaces to be stable. Another flaw type is crossing. So this is where you have a file that depends on many other files in the system. So you see this horizontal stripe of dependencies, and many other files in the system depend on it, a vertical stripe of dependencies. So again, it's a crossing. This is high fan in, high fan out is another way of saying this. There are modularity violations. Here's an industrial project that we analyzed, and when we looked at the structural dependencies between this set of files, you can see there's almost nothing. So this looks like a highly decoupled system. Excellent. However, when we add in history information, what we see is these files have very high history dependencies. So there's very strong historical coupling between 2 files. That typically means the files have shared secrets or some dependency that is not expressed in an interface that is not abstracted out. So whenever I change A, I have to change B. So one example I looked at a couple of years ago was an example from OpenSSL. There was a denial of service attack that was mounted on OpenSSL, and the problem was that OpenSSL did not limit the maximum key size for encryption. So an attacker could request an encryption with 1 million bit encryption key, and the system grinds to a halt, right? The website, the e-commerce website grinds to a halt. So, okay, they figured out the problem. They said, okay, what we need to do is go in and put a limit on the maximum key size that someone can request. What modules in OpenSSL need to be changed? Well, it turned out there was about 20 of them. And it took them 8 commits before they found them all and before they got them all right, because they didn't know about this assumption. This was a modularity violation. This information was not modularized. And we see flaws in every non-trivial project that we look at. So here's an example from JBoss. So here you see the JDBC Store Manager, which aggregates a set of classes, command and cache classes. But the command and cache classes themselves aggregate JDBC Store Manager. So there's a cyclic dependency among those files. Here we can see a set of dependencies between the command classes and relation database manager. So these are in a modularity violation flaw with each other. Here's an example from Apache Cassandra. So here you can see another example of an unstable interface. There's a leading file and many, many other files depend on it and change very frequently with it. Here's an example of a modularity violation. And here's an example of improper inheritance. You have a child class inheriting from a parent class and the parent class depending on the child class. So all of these are violations of proper design theory. So a research question then is, what's the consequence of these flaws? If a file is involved in greater numbers of issues, is it more error-prone? Is it more change-prone than average files? And so we took a look at a set of open source projects. These are mostly Apache open source projects, one commercial project as well. And what we did is we just counted, file by file, the number of architectural flaws that each file participated in. So if a file participates in a modularity violation, count it as 1. If it also participates in a cyclic dependency, now it's 2. If it also participates in an unstable interface, now it's 3. So we counted the number of flaws that each file participates in, and we also calculated the number of bugs that file has been committed to fix, the number of changes the file has been committed to implement, and the number of lines of code committed to fix those bugs and implement those changes. And there's the results. Clear? Okay, sorry. Let's zoom in on one of those projects. So this is Apache Avro, and what you see here is on each row the number of architectural flaws and the average number of bugs, bug churn, changes, and change churn for files within Avro that had that many flaws. So you can see for the files that participated in 0 architectural flaws, they had almost no bugs, they had almost no changes. But as you go down, you look at the set of files that participated in 1, 2, 3, 4 architectural flaws, look at 4, those files on average participated in 16.5 bugs, requiring 255 lines of code to fix, 33.5 changes requiring 1,220 lines of code. So for all of these projects, the number of flaws and the number of bugs, changes, and the amount of churn is highly correlated, always a 0.9 correlation. In a subsequent paper, we said, well, I wonder if this holds true for security flaws as well, because security flaws are particularly costly, particularly pernicious, damaging to reputations, costly. And so we did the same thing. We took, in this case, 11 projects, and we did the exact same analysis, but we also looked at the frequency of security bugs and changes made that were labeled as security, and we see the exact same kind of correlations, that security bugs are indeed strongly correlated with architectural flaws as well. These things are a problem. Finally, I'm nearing the end of my talk, how do we quantify the costs? What's the cost of the debt that you're carrying? So we want to look at these flaws, we want to look at the damaged parts of the architectures, parts that are causing your boat to be full of water and keeping you from making forward progress. And then we want to estimate the ROI, the return on investment, of fixing that, because really that is the bottom line. If I were to spend the money, invest the money to clean up this code base, is it going to be worth it? Right? That's what your boss's boss wants to know. So what we can do is, based on the analyses that we can do with this tool suite, we can look at individual DR spaces, individual clusters of files that are known to be highly buggy or highly change prone. We can identify the flaws in those clusters of files, and by identifying the flaw, you essentially identify a refactoring strategy. If there's a cyclic dependency, break the cycle. If there's improper inheritance, there's typically some functionality in a child class that needs to get moved up to the parent class. If there's a modularity violation, if there's a modularity violation, modularize that piece of knowledge, abstract that important piece of information. So we could identify the penalty caused by the architectural debt in terms of additional defects, additional changes, additional lines of code committed. And we can, by identifying the refactoring strategies, we can ask the architects to estimate the cost of doing the refactoring. How much would it cost you to modularize this information or to break that cyclic dependency? And using that information, we can come up with an expected savings. The assumption here is that if changes, churn, bugs are highly correlated with flaws, 0.9 correlation, if we remove the flaws, these files should go back to being normal files in the project. So they should have average project-wide levels of bugs and changes. So the difference between their current level and the average level is the expected savings that you gain from refactoring. And based on this, we can come up with a return on investment. So this was a project that we did with SoftServe, a global consulting company. And in this project, the cost of refactoring was estimated to be 14 person months. The benefit was calculated to be 41.35 person months per year, a 300% return on investment in the first year alone. This was a no-brainer to go to management and say, let's clean up the debt. We just had a paper published in ASE 3 weeks ago on our industrial experience, and also I hope you will go attend my colleague Wu Wansheng's talk tomorrow about the industrial experience we had with Huawei. So I won't talk about that because I don't want to steal his thunder, but I'll talk about the experience we had with ABB, where we looked at applying architectural level metrics, decoupling level, architecture flaw analysis, and cost-benefit analysis at 8 projects within ABB at different locations around the world, different sizes, different languages of implementation. And we asked them, does this help? So this gets to the final part of my research methodology, is the surveys and the interviews. Did this help to decide if, when, and where to refactor? Did it help practitioners figure out, does my project suck? Right? Am I really bad compared to other projects within the company or around the world? And does the tool suite really help me find the source of the problems? So these are the 8 projects with, of course, identifying information removed to protect the guilty. This one at the bottom, Project EC, had a decoupling level in the 28th percentile. It was extremely confirmed by the architects to be extremely difficult to maintain. They said that a 1 line of code change could take a person-month of effort in this project. And of course, we were able to find lots and lots of architectural flaws like cliques and unstable interfaces and modularity violations. And the files that participated in these cliques were in typically the top 1% or top 0.1% of the buggiest files of the project. So they were the most error-prone files. We also talked to the ABB architects, and we asked them things like, well, what did this information reveal to you that you didn't know about your architecture, and were these metrics useful? So they verified that the information we provided was useful in closing the gap with management. It is often the case that architects know in their gut that something is wrong, but being able to precisely identify it and quantify it gave them a tool that they had not had before. So these quantifiable results helped them to make the case that the flaws were the cause of maintenance difficulty. This architecture degradation was the cause of maintenance difficulty. 6 of the 8 projects did plan or had already, in fact, started the refactoring process. So the lessons learned? Yes, it is possible to objectively assess and quantify architectural quality. Where I began with SAM and ATAM was a good start for the 1990s, but we've moved beyond that, and I think justifiably so. And it's possible to bridge the gap between the money people and the architecture people. These results were enthusiastically received. The project were taking action on it, and they are incorporating this into their regular build process. So final thoughts. You can't manage it if you don't measure it. Quantification is key. And this measurement has to be automated. If it relies on the skill and knowledge and time of individuals, it won't be done, or even if it's done, it may not be trusted, it may not be repeatable. It's really useful to incorporate these into a regular build process, just the way you might do regression testing. You might do security scans in your nightly build. And this eventually leads to early notification and eventually improved architectures. And in the end, money talks. It's the only thing that really is universal among all the stakeholders. And so quantification and return on investment calculations are critical. So with that, I'd like to thank you, and I'm happy to take questions.
Does anybody have any questions?
Thank you for this very interesting talk, really. You showed us the results that the architectural flaws correlate with the metrics like bug churn and so on. I was wondering what happens if you remove the architectural flaw. Does the file still have high bug churn, which means there's another cause for the bug churn and it just happens to be a correlation, or is that the next step maybe to do?
Yeah, so it's a great question. We've actually been doing a number of refactoring studies where we look at the before and after state. And indeed, we do see that when you remove the flaws, the rate of new bugs introduced goes down. Now, you have to be careful how you analyze this. If you look at the entire history of that file, it has all of that bad stuff there. So you have to, divide history into a before and after segment. But when you do that, yes, we have seen that correlation in this case really does look like causation.
Okay.
And so when you remove the flaws, the architecture becomes easier to maintain, easier to modify, easier to understand. Thanks.
Hi, Rick. Thanks very much for a great talk. My name is Alberto Ritzer, Isolab Solutions. I really appreciate the history that you showed going from architecture reviews to automation. And my question is, to what extent automation can replace the benefits you used to get in architecture reviews, where we got all the architecture team together, we got the buy-in, you got the feedback and so forth?
Right, that's a great question, thank you. So for those of you that didn't hear it, Alberto's question was, to what extent do these automated measures replace architecture reviews? And I would say they're complementary. An architecture review has a lot of benefits, and this is something that we learned over the years in doing SAMs and ATAMs and CBAMs, all the AMs, is the architecture reviews bring people together. Often it brings the stakeholders together for the very first time, and that's when you get the programmers and the managers and the testers and the integrators and the customers all in the same room talking more or less the same language. And that has a lot of benefits for a big project in terms of getting buy-in for the architectural vision, getting a community of support for the architect, clarifying requirements, clarifying trade-offs. So I would not say that this is a replacement for that, because there's so many benefits from a community aspect that come from doing an architecture review where actual people talk to each other. That's good. However, what that lacks, and what you typically cannot do in an architecture review, which is a day or a half a day or 2 days long, is you can't get precision. So there's no such thing as an ATAM where we said, oh, your mean time to failure will be 230 days, or your average latency on this important use case will be 600 milliseconds. We can't get any kind of precise results from these architecture reviews. We identify trends. So I see these as complementary techniques. One gives you great precision. It gives you repeatability. As I say, you can put it in the nightly build process and associate alarms with certain, if I have a new architecture flaw that appeared since yesterday, I want to report, I want to know about it. If my decoupling level falls below this particular threshold, maybe it's time to do a refactoring. Those kinds of benefits accrue to an automated technique, which won't accrue to the human-oriented analysis method. So I do see them as being complementary.
So thank you, Rick, for the nice talk. I'm Ralf Reusner from KIT in Karlsruhe. I'm wondering, as you analyze the code of the open source project and try to derive the architectural structure out of that, you basically have the architecture as a description what is there. But we often use, of course, architectural knowledge of fragments as the architecture as it ought to be, which is obviously not what is in the code.
Yes.
And now I understand you have anti-patterns, you try to, from the data you have, you try to find things which are obviously not good, and we know that from experience.
Yeah.
However, I'm wondering, would your approach benefit from adding information about the architecture as it ought to be, because you find even more violations and even more misplaced decisions and so on? Or do you think at the end of the day, I probably got it all with the anti-pattern detection?
Yeah, that's a great question. So in fact, one of the things that I've been working on, and lots of other people have worked on this as well, I know, is trying to do automatic pattern recognition in an architecture, and in fact to do fuzzy pattern recognition. So we expect there to be an adapter pattern or a factory pattern, but it wasn't implemented very well, and so if we try and do precise pattern matching, it won't match. So we, in fact, are using this notion of a design rule space to do this fuzzy pattern matching. So if I have a file called blah blah factory, that sounds like a design rule. And so we're going to look at the set of files that are in its DR space and try and identify the relations between those files as a fuzzy pattern match, and then compare the as implemented with the as intended. So yeah, absolutely, that kind of as intended architecture is really important because that's what's in the architect's head. We think that we have 5 layers. In fact, we have big ball of mud, but somehow we've grown up believing we have 5 layers. So yeah, that's a really good insight. Thank you. Oh, okay, here first.
Just to be pretty last, have you done some study to relate the information that you gather here and you correlate it to, I don't know, business impact factors and in very large systems? You might have some components or features of the system which have key aspects of impact of business. I don't know. This company is doing, I don't know, this now is doing online sales. There was the offline sales, but now the online sales is the main thing. The offline sales is done.
Yeah.
So have you done some correlation? Okay. So if there are both in the offline side of the sales, this is not going to be as important as dealing with the online sales system. So is there part of your study where you correlate the impact to business to the impact in the
Yeah, that's a great question, and the answer is yes and no. In the end, what we do when we're working with industrial collaborators is we prepare a report, and the report says, here's all the dirt we dug up about your architecture. It has these flaws. These flaws are costing this amount of debt per year. Here's the decoupling level. Here's potentially some refactoring strategies. And then we give it back to the business, and the business looks at it and typically says something like what you said, like, you know, I care about this, I care about this, don't care so much about that and that, because perhaps there's some dusty corner of the architecture that isn't being actively worked on. So to some extent, we just leave that up to them to make that determination. You know, kind of, again, like your doctor telling you you have high cholesterol and you decide whether you want to cut down on milkshakes or not. But we can provide some insight into that, and this comes from the history analysis. So in the history analysis, we can look at the trends of the files, and we can essentially take time slices of a system's history. And so if we see that there's an area of the architecture which has flaws, but where that area has not been active in the previous year or two, that would be an indicator back to the project that perhaps this isn't an area that's going to bring them much return on investment. So we can at least hint at the kind of insight that you're asking for. The problem, the reason it's only a hint, is it takes a while to build up enough history to really see those trends. And they may just know because they know the business. They may know more than what we can discern from those trends.
Hi, thanks for your talk, Rebecca Orsbrock. I have two questions. The first one, maybe you can answer quickly, but talking about design flaws, you talked about things like inheritance or whatever, you know, at that granularity. But have you developed metrics for functional programming styles that are getting prevalent? And then the other question was, you know, thinking from an industrial standpoint, the stability or the correlation between the libraries I'm using, because a lot of people use open source, and the architectural flaws that introduces into their architectures. So thoughts about those two things.
Yeah, so I don't think I understood the first question. So let me answer the second question first, and then maybe you can. So the question about libraries, sure, that's a huge concern because, as you say, nobody builds systems from the ground up. Everybody builds on other systems. And so, in fact, a recent project has been to try and assess the quality of libraries or frameworks or components. And what we do is we use this analysis as one of the dimensions of analysis. So we're trying to do a kind of consumer reports. I don't know if that means anything to people from Europe, but it's a consumer agency that does product ratings in the US. And they'll provide essentially tables of rankings along various quality measures. So if you're trying to buy a new car, they'll talk about the gas mileage of the new car and its safety rating and its crash worthiness and its carrying capacity and so forth. So we're putting together these scorecards for components along multiple dimensions. One of those dimensions is the modifiability, maintainability dimension. Sorry, I still don't understand your first question.
Well, so you talked about design flaws that you detected in various modules, and I'm wondering if you've done anything for functional style programming, you know.
Oh, I see what you're saying. So, okay, for
because objects are not the only implementation technology, so just wondering about that.
Yeah, we have not. So presumably there would be a different set of characteristic flaws in a functional programming language. And so we would simply need to formally model what those relationships were, and we could use the same tooling. So each of the flaws that we detect has a formal representation, which allows us to plug it into a tool, which then examines the DSM to find that pattern. It's essentially a pattern matching process. So we don't have those patterns, but I think it would be extensible to that. Maybe we can talk about that. She's my wife, so I don't know what kind of question it is. It's just scary.
So this is not a planned question, by the way, but great job. So my question is that with this kind of tool, you discover those architectural flaws. So from the organizational perspective, it's great, right? You can do some refactoring and fix those spots. But I'm more interested in your experience. Are there some resistance of using the tool? Because the people that are responsible for those flaws, they are in hard seat, right?
Yeah.
Kind of?
Yeah, so actually, I mean, maybe you attend tomorrow's talk to hear about that, about the adoption of these kinds of things. But what we've been finding is generally not. So architects often feel pressured on many sides. They feel that there are these unreasonable management expectations on them to always do more. There are expectations from their stakeholders. They're dealing with this group of unruly programmers. And so typically I've found they've been very receptive to this kind of information because, as I said before, they feel it in their gut. They know, an architect knows when their architecture is horrible, when it's hard to maintain, it's hard to debug, it's hard to understand, it's hard to extend. And this, for the first time, often gives them the hard, cold evidence to say, yes, it's terrible, this is how terrible it is, this is how we compare to other similar systems, and we actually have a path, a strategy that we could use to address this terribleness and improve it. And as I said, this sort of arms them with evidence that they can take to management, and they can argue for getting that budget and schedule for refactoring. Almost always, as I said earlier, management doesn't want to pay for refactoring because they see it as budget and schedule used up for no new features. And features are really what they care about, what their customers care about. So it's really difficult argument to make, and this arms the architect with some evidence as to why they really should make this investment. It's kind of like, if you never do an oil change on your car, everything's great and you're saving money until the engine seizes up and catches on fire. But until that point, you're ahead, right? I never had to go to the mechanic. I never had to pay a penny for oil changes. Until the car stops, you're doing great. And so it's giving them that kind of evidence that says, you know, a little bit of prevention now would really pay us back greatly in the future.
Okay, so my name is Pablo Antonino. I'm from the Fraunhofer Institute in Kaiserslautern, Germany. We deal basically, actually my department, with architectures for embedded systems. And the stakeholders that we have, so to say the architects, they are quite non-trivial, so to say. Basically, these guys are electrical engineers, mechanical engineers, even physicists, so to say. And it's pretty hard to convince these guys that they should, let's say, think on the aspects that you put here to design the architectures that we support. We're talking about systems that will run in a controller, in a sensor, or very, so to say, dedicated software.
Yes.
This is one side. So last week, I read something very interesting from one Spotify architect, and he claimed that a great architecture from the point of view of Spotify is when they can plan, design, implement, and deploy that in 1 week. Maybe this can be a realistic for Spotify or for information systems, but for embedded systems, this is absolutely out of question. Unfortunately, this is not realistic. Yeah. Now I come to my question based on these two statements, so to say. Do you believe that the statements that you put in here to assess the quality or how healthy is an architecture, would it apply for embedded systems, or would you have to revisit these items? Thank you.
Sure. So absolutely applies. So the kinds of systems that Huawei is building, these are embedded systems. The ABB examples that I gave, those are embedded systems. So many of the examples that we've studied have been embedded systems, and for just the reasons that you said, that these are complex, that once you ship, the cost of making a change is much higher. For many reasons, you should probably be paying even greater attention to architectural quality than in systems where it's relatively easy to ship another release, another release, another release. So I think that there has been a tradition in these embedded systems of the hardware designers running the show. And that's just, you know, a historical artifact. And so I think we need to make the argument for why that needs to change. And in many organizations, they realize that and they accept that. But you cannot, with the complexity of these systems as they are, you can't just hack your way out of problems. You know, I always give the example, if you had a building like this that you were building, a big building, multiple stories, and you said, well, what we're going to do is we're going to start digging a foundation, and we're going to start pouring cement, and then we're going to start welding some steel together, and then we'll start thinking about what we want the building to be and how it should function. You know, that's laughable, right? It's laughable in any other engineering discipline. So it's actually a little bit discouraging that we still have to make this argument in software engineering that doing some analysis is a good thing, and doing it early, doing it often is a good thing. So I do think that we can and should make this argument. And when you provide the evidence, and when it is repeatable and reproducible, sensible people accept it and adopt it. Thank you.
Hi, I'm Nabu from University of Fortaleza, Brazil. Thanks for the talk. My question has to do with the code from Spotify that my colleague just mentioned about agility. So if you could say a few words about your work and your tools and your experience in this new wave of developments that are gaining popularity in the industry, microservice, DevOps, where the complexity is supposed to be moving away from source code
Yes.
but to the runtime and operations. For example, does it still make sense to analyze code changes from the source code? The steps are so simple. Perhaps you should analyze like logs from the continuous delivery pipeline. So which servers are being redeployed together. And also, finally, I mentioned in the beginning of your talk, you mentioned about misalignment between academia and the industry. I think now we have like a forced alignment because academia is falling behind trying to do like research of microservice. And I've seen some papers submitted on microservice that have like the evaluation is like a couple of servers deployed in a couple of machines.
Yeah.
So we are forcing the alignment, but we are still irrelevant to the industry. So you could say a few words about those new developments. Thanks.
So, so your point about microservices is a great one. As we move towards more dynamic architectures, let's say, if I can use that as a sort of generic term, architectures where at least the allocation of resources is not determined until runtime, then we need different mechanisms to discern dependencies, because A does not call B in a programming language sense. It's not a method call or something. It's going to be a message. Maybe it's a pub sub or through a broker or through some other mechanism. So we need different extraction tools to determine the dependencies, which are often only established at runtime. However, once we have that information, the analyses can proceed exactly the same. A dependency is still a dependency. And so if you have a cycle of dependencies, that's probably a bad thing, whether that was via method calls or via some runtime relationship. Now I've forgotten the second question. Something about the relationship between academic and industrial research. Sorry.
Because you talk about the misalignment between industry and academia in the beginning, and now the academia is falling behind.
Yeah, so so this is more an issue of policy. I've been involved in ICSI, in the ICSI steering committee, trying to get a greater emphasis on industry. I think this past ICSI in Gothenburg did a great job on inviting industry in and having events that increased industrial participation. And I try to attend 1 or 2 industrial conferences a year so that I'm listening to the problems of practitioners and their solutions, because as I mentioned, and as you said, sometimes they're ahead of us in academia. This is not a technical problem to solve. This is a social problem where we cannot remain in our enclaves and not listening to each other, especially in software engineering, right? We're an engineering discipline, and that means we have to be focused on problems of practical significance. If we don't understand practice, shame on us. So I think doing things like industry days, I think all of us should attend some industry symposia as something that's healthy for academics and software engineering to be doing, to hear their problems, to hear their solutions, to discuss collaborations. Some of my most exciting work, I think, is when I'm collaborating with people in industry on real problems of real significance. That's what makes me happy anyway.
I think you've already answered 2 of my questions, but I was wondering if you had a correlation with architectural patterns, such as the layers pattern, MVC, event-driven or hexagonal, those kinds of patterns. I also had microservices and MapReduce here, but I think you've answered those 2.
Oh, there you were. Trying to figure out who was talking.
Yeah, sorry about that.
Okay, so the question is, what's the relationship between the anti-patterns that we found and the kind of patterns that we intentionally design into our architecture? Yes?
pretty much. What's the health correlation you find with these architectural styles?
Right. So this takes us back to this notion of a design rule and why we initially became interested in the design rule space as our analysis lens, is that design rules give us intellectual control over ever-increasing complexity. They allow us to partition things. They manifest the power of abstraction. Specific patterns, what do I want to say? Specific patterns do not have specific architectural flaws. So any pattern can participate in any architectural flaws. So the architectural flaws are orthogonal to the pattern. It's important to be able to identify the pattern, but we don't need to identify it in the sense of identifying the unique flaws of that pattern. Flaws tend to be a relatively small number, at least over all these years of research, we've only found identified six types, and these account for the vast majority of bugs. But having said that, identifying the design rules and the impact of the design rules is really useful and really powerful. We did about 3 or 4 years ago, we published a paper in the Conference on Software Engineering Education and Training. And what we did is we did a course in design patterns at 3 different universities. We taught the students, for an entire semester, we taught them design patterns. At the end of the semester, after a set of increasingly complex assignments, we gave them a UML diagram for a game that involved 3 or 4 patterns that they had been previously taught. And we said, go implement this game. Then we analyzed the code that they implemented. Roughly 3/4, I think it was 78% of them violated at least one of the patterns. Right? So this is the best possible case. We just finished a semester-long course. We gave them the UML diagram, and they still got the pattern. They implemented the patterns wrong about 3/4 of the time. So I love patterns. I think they're really important. But if you cannot analyze them automatically, the flaws will just breed. They'll just grow. I hope I answered your question. Okay, meet me in the break.
Thank you very much, Rick.
Thank you.
Here we have free presents for you. I hope that you enjoy from the organizing, also from UPM. And this is for you. Thank you very much for coming.